Summer 1945. Chkalov Airfield, 70 miles east of Moscow. Soviet test pilot Major Pyotr Stefanovsky circled the massive American fighter for the third time that morning, his boots clicking against the concrete as he studied every rivet, every panel, every curve of the aircraft that had just changed everything he thought he knew about aerial warfare. The Republic P-47 Thunderbolt sat on the tarmac like a defiant monument to American industrial philosophy, its enormous radial engine cowling catching the early sunlight. Stefanovsky had flown every fighter in the Soviet arsenal. He had tested captured German Messerschmitts and Focke-Wulfs. He had pushed the boundaries of the Yak-3 and the La-7, but nothing, absolutely nothing, had prepared him for what he was about to discover. This wasn't just another fighter aircraft. This was a statement, a declaration, a philosophical argument made of aluminum and steel that would force the entire Soviet aviation industry to confront an uncomfortable truth. Sometimes, overwhelming firepower and engineering redundancy defeated elegant simplicity. Sometimes, the American approach simply worked better. Before we jump back in, tell us where you're tuning in from, and if this story touches you, make sure you're subscribed, because tomorrow I've saved something extra special for you. The Thunderbolt had arrived at Chkalov through the complex channels of wartime alliance and accident. Throughout 1944 and 45, dozens of American aircraft had made emergency landings on Soviet territory. Damaged B-17 bombers returning from raids over Germany, P-51 Mustangs that had strayed too far during escort missions. But this particular P-47D represented something different. Lieutenant James Mackenzie of the 356th Fighter Group had been forced down near Poltava in Ukraine during a shuttle bombing mission in August 1944. His Thunderbolt, nicknamed Big Iron, had taken flak damage over Romania but remained remarkably intact. Soviet recovery crews had transported it carefully through rail lines to Moscow, where it joined a growing collection of Allied aircraft at the Scientific Research Institute of the Air Force. The NIIVVS, as it was known, represented the Soviet Union's most advanced aeronautical testing facility. Here, captured German jets were being evaluated. Here, American Lend-Lease aircraft were being studied for potential license production. And here, Soviet engineers would confront aircraft that challenged their fundamental assumptions about fighter design. Major General Viktor Bolkhovitinov, director of the NIIVVS, had assembled his best team for the Thunderbolt evaluation. Stefanovsky, as chief test pilot, whose experience encompassed over 200 aircraft types. Engineer Colonel Alexander Yakovlev, nephew of the famous Yakovlev who designed Soviet fighters bearing his name. Armament specialist Captain Igor Shelikov, who had studied every weapon system the Luftwaffe possessed. Propulsion expert Lieutenant Colonel Georgy Balandin, whose understanding of radial engines was unmatched in Soviet aviation. They approached the Thunderbolt with the confidence of engineers from a nation that had just helped defeat Nazi Germany. Soviet fighters had ruled the Eastern Front. The Yak-3 had outmaneuvered every German fighter. The La-7 had combined speed with firepower. Soviet aviation had proven itself in the crucible of combat. How much could they really learn from this massive American machine that seemed to violate every principle of Soviet fighter design philosophy? The answer would humble them completely. Stefanovsky's initial walk-around inspection revealed the first shock. The P-47D weighed 7 tons empty. 7 tons. The Yak-3, the Soviet Union's premier fighter, weighed barely 2 tons. The Thunderbolt weighed more than 3 Yaks. More than some Soviet medium bombers. For a single-seat, single-engine fighter, this seemed absurd. Soviet design philosophy emphasized lightness, agility, simplicity. Keep the weight down, maximize maneuverability. Make the aircraft easy to produce, easy to maintain, easy to repair in field conditions. The Americans had apparently read a different manual entirely. They had built a fighter that seemed to embrace weight, complexity, and redundancy with almost reckless enthusiasm. But as Stefanovsky climbed into the cockpit for the first time, certain details began shifting his perspective. The armor plating behind the pilot's seat was nearly twice as thick as Soviet standards. The bulletproof windscreen could stop 20mm cannon shells that would shatter Soviet glass. The self-sealing fuel tanks contained multiple layers of protection. The control cables were duplicated and triplicated. The hydraulic systems had backup systems for the backup systems. This wasn't just an aircraft. This was a fortress that happened to fly. Engineer Colonel Yakovlev spent 3 days examining the Thunderbolt's structure before making his initial report. His findings challenged everything Soviet designers believed about aircraft construction. The Americans had used 7,000 rivets, where Soviet designers would have used 3,000. They had employed aluminum alloys with tensile strengths 30% higher than Soviet equivalents. They had incorporated fasteners, joints, and connections that could be disassembled and reassembled dozens of times without degradation. Most striking was the wing construction. Soviet fighters used wooden spars in their wings to save strategic metals for engines and weapons. The Thunderbolt's wings were entirely metal, with stressed skin construction that distributed loads across the entire structure. Yakovlev's calculations revealed that these wings could sustain G-forces that would tear Soviet fighters apart. During violent combat maneuvers, in high-speed dives, during desperate evasive actions, the Thunderbolt's pilot could push the aircraft beyond limits that would kill pilots in lighter, more agile fighters. It was a revelation that cut to the heart of combat philosophy. What good was superior maneuverability if your aircraft disintegrated when you used it? What value was elegance if it meant fragility? Lieutenant Colonel Balandin's examination of the Pratt & Whitney R2-800 radial engine produced even more dramatic realizations. The engine displaced 2,800 cubic inches, produced 2,500 horsepower with water injection, and weighed over 1 ton by itself. Soviet radial engines producing similar power weighed 500 pounds less. But Balandin discovered something that made that extra weight worthwhile. The R2-800 could sustain damage that would destroy Soviet engines and continue operating. Cylinders could be shot away completely, and the engine would run rough but keep running on the remaining cylinders. The supercharger could be damaged, and the engine would lose altitude performance but maintain sea-level power. Oil lines could be severed, and the engine had reserve capacity in multiple locations. Cooling systems could be compromised, and the massive aluminum cooling fins would dissipate enough heat to prevent immediate seizure. Balandin tested the engine at full power for 6 hours continuously, far exceeding standard Soviet test protocols. The engine temperature stabilized, the oil pressure remained constant, the power output never wavered. Soviet engines tested under similar conditions typically showed degradation after 3 hours. The R2-800 seemed capable of running forever. When Balandin finally shut down the engine and disassembled it for inspection, he found minimal wear on critical components. The Americans had engineered tolerances, metallurgy, and lubrication systems that simply outlasted Soviet equivalents. This was engineering philosophy made manifest. Build it strong enough that it doesn't break. Make it reliable enough that pilots trust it absolutely. Create redundancy so that battle damage becomes survivable rather than fatal. Preparing and narrating this story took us a lot of time, so if you are enjoying it, subscribe to our channel. It means a lot to us. Now, back to the story. But the armament evaluation produced the most profound shock. Captain Chkalov approached the Thunderbolt's weapons with the skepticism of a man who had seen every German fighter gun, every Soviet cannon, every captured Allied weapon that had passed through NIIVVS. Soviet fighters typically mounted 1 or 2 20mm cannons and 2 or 3 12.7mm machine guns. The Yak-9T carried a single 37mm cannon firing through the propeller hub, devastating when it hit but limited by rate of fire and ammunition capacity. German fighters had progressed to 30mm cannons. The Americans had apparently decided to ignore cannons entirely and go in a completely different direction. The P-47D mounted 8 Browning M2 50 caliber machine guns, 4 in each wing. 8 guns, each capable of firing 800 rounds per minute, each loaded with ammunition belts containing armor-piercing incendiary, tracer, and ball rounds in carefully calculated sequences. Chkalov did the mathematics and found himself recalculating because the numbers seemed impossible. Maximum theoretical rate of fire, 6,400 rounds per minute combined. That was 106 rounds every second. In a 2-second burst, the standard firing duration for aerial combat, the Thunderbolt would put over 200 heavy machine gun bullets into the air. Each 50-caliber bullet weighed 45 grams and traveled at 850 meters per second. The kinetic energy delivery per second exceeded anything Chkalov had calculated for any fighter aircraft in existence. The ammunition capacity proved equally staggering. The Thunderbolt carried 3,400 rounds total, 425 rounds per gun. At maximum rate of fire, that provided approximately 30 seconds of continuous shooting. Soviet fighters typically carried enough ammunition for 10 to 15 seconds of firing. German fighters averaged 20 seconds. The Americans had simply decided that running out of ammunition was unacceptable and engineered a solution regardless of weight penalty. But capacity meant nothing without accuracy and reliability. Chkalov prepared for live-fire tests with the expectation of discovering typical weaknesses. Guns that jammed in cold weather, feed systems that malfunctioned during aerobatic maneuvers, synchronization problems that resulted in pilots shooting off their own propellers. What he discovered instead was a weapon system that had been engineered with the same obsessive redundancy as the rest of the aircraft. Each gun was independently mounted, independently fed, independently cocked, and independently fired. If one gun jammed, the other 7 continued firing without interruption. The ammunition feed systems used revolutionary disintegrating link belts that eliminated the jamming problems of older fabric belts. The gun heating system used ram air cooling that increased effectiveness at high speeds. The harmonization, the convergence point where all 8 guns concentrated their fire, could be adjusted precisely for different combat ranges. The first live-fire test occurred on a cold October morning in 1945. Stefanovsky took the Thunderbolt to 15,000 feet, spotted the ground target, a captured German Panzer Mark IV tank positioned on the test range, and rolled into his attack dive. At 400 miles per hour, 800 yards from target, he pressed the trigger. The aircraft shuddered. The wings seemed to vibrate. The cockpit filled with the sound of mechanical thunder. Through his gun sight, Stefanovsky watched the tank simply disintegrate. The first burst, lasting less than 2 seconds, punched through the tank's armor like it was paper. Armor-piercing incendiary rounds penetrated the hull, exploded inside, and blew the turret 15 feet into the air. Stefanovsky pulled up, circled, and made a second pass at a truck convoy target. Another 2-second burst. 3 trucks exploded simultaneously, their fuel tanks ignited by incendiary rounds, their frames shredded by armor-piercing bullets. He had fired perhaps 5 seconds total. He had destroyed targets that would require multiple passes with Soviet fighter armament, and he still had ammunition for 25 more seconds of firing. Stefanovsky landed the Thunderbolt, shut down the engine, and sat in the cockpit for several minutes, processing what he had just experienced. Finally, he climbed down and found Captain Chkalov waiting with his assessment. The captain's face showed the expression of a man whose fundamental assumptions had just been demolished. Chkalkov's report, submitted to the NII-VVS leadership 3 days later, pulled no punches. The Americans had achieved firepower concentration that exceeded anything in Soviet or German arsenals by abandoning cannon-caliber weapons, and instead engineering a solution through overwhelming volume of fire. While Soviet and German designers debated the merits of 20mm versus 30mm cannons, arguing about muzzle velocity and armor penetration and ballistic efficiency, the Americans had simply mounted 8 heavy machine guns and called it solved. The philosophical difference was stark. Soviet fighters were designed around precision. A skilled pilot with a 37mm cannon could destroy any aircraft with a single well-aimed shot, but that required skill, timing, perfect deflection shooting, and split-second opportunity. The Thunderbolt's philosophy eliminated the need for such precision. Fire a 2-second burst. Put 200 rounds into a cone of space. Something in that cone will die. It was industrial firepower replacing artisanal accuracy. It was American abundance overcoming European efficiency. And as Shellikov's report concluded with remarkable honesty, it was devastatingly effective. A mediocre pilot in a Thunderbolt could achieve kill rates that would require exceptional skill in a Yak or La fighter. The aircraft compensated for human limitation through mechanical superiority. This was a weapon designed for a citizen air force, not an elite cadre. This was democracy's fighter. The NII VVS testing program continued through winter 1945 into early 1946. Stefanovsky accumulated over 60 flight hours in the Thunderbolt, pushing it through every performance regime, every tactical scenario, every combat maneuver in Soviet doctrine. The accumulated data produced a portrait of an aircraft that succeeded by violating nearly every principle Soviet designers held sacred. Speed? The Thunderbolt's maximum speed of 430 miles per hour at altitude was respectable but not exceptional. Soviet La-7 fighters could match it. German jets exceeded it easily, but the Thunderbolt could maintain maximum speed for hours. Soviet fighters pushing maximum speed for extended periods risked engine failure. The Thunderbolt just kept going, the massive radial engine running cool and smooth regardless of throttle setting or altitude. Climb rate? The Thunderbolt's initial climb rate was mediocre, worse than most Soviet fighters, but at altitude above 20,000 feet, the turbo-supercharged R2-800 delivered full power, where Soviet engines gasped for air. The Thunderbolt actually climbed faster at 25,000 feet than at sea level. No Soviet fighter could match that. Maneuverability? The Thunderbolt could not turn with a Yak-3. It could not roll as quickly as a Focke-Wulf 190, but its controls remained responsive at speeds where Soviet fighters became sluggish and dangerous. In a high-speed dive, exceeding 500 miles per hour, the Thunderbolt's controls still responded crisply. Soviet fighters at such speeds often became uncontrollable, their control surfaces locking up due to aerodynamic forces. Dive performance revealed the Thunderbolt's most dramatic advantage. Soviet fighters were limited to dive speeds around 450 miles per hour before structural concerns became critical. The Thunderbolt could dive at over 550 miles per hour safely, and test pilots had taken it beyond 600 miles per hour in emergency situations without structural failure. This meant that in combat, a Thunderbolt pilot being pursued could simply push the nose down and dive away from virtually any opponent. Soviet fighters attempting to follow would either pull out early or risk catastrophic structural failure. It was an escape option that fundamentally changed combat psychology. Thunderbolt pilots knew they could always dive away if overwhelmed. That confidence affected everything, making them more willing to engage, more aggressive in pressing attacks, more likely to survive mistakes. Range and endurance produced similar revelations. The Thunderbolt's internal fuel capacity of 370 gallons, expandable to 490 gallons with external tanks, provided combat radius exceeding 400 miles. Soviet fighters averaged 200-mile combat radius. The Germans were similar. The Thunderbolt could fly escort missions deep into enemy territory, engage in extended combat, and return home with fuel to spare. Stefanovsky flew a test mission that lasted 4 hours 20 minutes, including 30 minutes of full-throttle combat simulation. He landed with 45 minutes of fuel remaining. No Soviet fighter could approach such endurance. Survivability testing produced results that fundamentally challenged Soviet aviation philosophy. Engineer Colonel Yakovlev designed a series of live-fire tests where captured German weapons fired at the Thunderbolt structure to simulate battle damage. 20mm cannon shells hit the wing leading edges. The armor plate behind the engine absorbed the impact. The wing structure remained intact. 30mm shells struck the wing center section. The stressed skin construction distributed the load. The wing maintained structural integrity. 13mm machine gun rounds peppered the fuselage. The self-sealing fuel tanks sealed automatically. The duplicate control cable systems maintained control authority. In one test, engineers deliberately severed 3 of 4 elevator control cables. The remaining cable, rated for 4 times the necessary load, controlled the aircraft normally. They disabled 3 of 18 cylinders on the radial engine. The engine lost 16% of power, but continued running smoothly. They punched holes in the oil cooler. The reserve oil capacity lasted long enough for simulated return to base. The Americans had engineered survival into every system. Soviet fighters achieving mission success relied on not being hit or not being hit in critical systems. The Thunderbolt assumed it would be hit and engineered itself to keep fighting despite damage. Yakovlev's final report contained a sentence that would be quoted in Soviet aviation design bureaus for decades afterward. The Americans do not build fighters. They build flying tanks that happen to have wings. But perhaps the most telling evaluation came from the pilots who flew both Soviet and American types. Major Stefanovsky had flown everything. He understood the Yak-three's beautiful handling, the La-7's powerful acceleration, the MiG-3's high-altitude performance. Yet when interviewed for his final assessment, his words carried weight precisely, because they came with no nationalist bias or political requirement. He was being asked for truth, and in the relatively open atmosphere of immediate post-war Soviet technical evaluation, he could provide it. The Thunderbolt represented a different philosophy of air combat, Stefanovsky explained. Soviet fighters were designed around the assumption that pilots would engage in traditional dogfighting, turning combat where agility and climb rate determined victory. The Thunderbolt assumed that pilots would use speed, altitude, and diving attacks, engaging when advantageous and escaping when not. Soviet doctrine emphasized pilot skill overcoming aircraft limitations. American doctrine emphasized aircraft capability compensating for pilot limitations. Neither approach was inherently superior, Stefanovsky argued diplomatically, but the American approach scaled better. Training a pilot to exceptional skill level required years. Building aircraft with exceptional capability required industrial capacity. The Soviet Union had skilled pilots but limited industrial capacity. America had nearly unlimited industrial capacity and could rapidly train adequate pilots. The Thunderbolt was the perfect expression of American strategic advantage. Captain Shelikov's armament analysis reached similar conclusions through different reasoning. Soviet fighters mounted limited ammunition and required pilots to make every shot count. This produced excellent marksmen but created vulnerability when facing numerous opponents. The Thunderbolt's massive ammunition load and 8-gun battery meant pilots could afford to miss, could fire longer bursts, could engage multiple targets sequentially. In combat against bomber formations, where multiple targets presented themselves simultaneously, this proved decisive. A Soviet fighter with limited ammunition might destroy one bomber before needing to disengage and return to base for rearming. A Thunderbolt could destroy 3 or 4 bombers in a single engagement and still have ammunition remaining. Shelikov had witnessed gun camera footage from American 8th Air Force missions over Germany. Single Thunderbolts had engaged entire German fighter formations, firing continuously, destroying multiple opponents through sheer volume of fire. Soviet doctrine said this was impossible. The footage said otherwise. The Americans had changed what was possible by changing what they were willing to carry, willing to build, willing to engineer into existence despite weight penalties and complexity. Lieutenant Colonel Balandin's final engine report provided perhaps the deepest insight into American versus Soviet industrial philosophy. The R-800 radial engine represented engineering abundance applied systematically. Soviet engines were designed to minimum specifications, achieving required power with minimal weight and resources. Every component was optimized for efficiency. The result was engines that performed beautifully when new but degraded rapidly under combat conditions. The R-800 was designed with massive safety margins. Components were overbuilt for anticipated loads. Tolerances were looser, reducing manufacturing difficulty but requiring heavier construction to maintain reliability. Redundancy was built into every system. The result was an engine that performed adequately when new but maintained that performance indefinitely. Soviet engines required skilled maintenance and frequent overhaul. The R-2-800 could be maintained by moderately trained mechanics with simple tools. Soviet engines degraded noticeably after 100 hours of operation. The R-2-800 showed minimal degradation even after 500 hours. In sustained air combat operations, where aircraft flew multiple missions daily and maintenance had to occur in field conditions under time pressure, these differences became decisive. American fighter groups could maintain operational readiness of 70 to 80%. Soviet fighter regiments averaged 50 to 60%. The engineering philosophy that seemed wasteful in laboratory conditions proved supremely practical in combat reality. The revelations from Chkalov Airfield rippled through Soviet aviation circles with unexpected force. By spring 1946, detailed technical reports on the Thunderbolt had reached every major design bureau in the Soviet Union. Artem Mikoyan, co-designer of the MiG series, spent 3 days reviewing the structural analysis. Semyon Lavochkin, whose La series fighters had dominated the Eastern Front, requested permission to examine the actual aircraft. Alexander Yakovlev, whose name graced some of the Soviet Union's most successful fighters, submitted a 30-page memorandum to Stalin's aviation commissar, analyzing the implications. The American approach challenged fundamental assumptions about how fighters should be designed, manufactured, and employed. More troublingly, it suggested that the Soviet Union's constrained industrial capacity might be a decisive disadvantage in any future conflict with the West. The debates that followed revealed deep divisions within Soviet aviation philosophy. The traditionalists argued that Soviet design principles had proven themselves in combat against Germany. Lightweight, agile fighters, optimized for turning combat, had defeated the Luftwaffe in the skies over Stalingrad, Kursk, and Berlin. Why abandon proven success to chase American concepts that violated basic physics? Heavy fighters were sluggish fighters. Complex systems were vulnerable systems. Over-engineering was wasteful engineering. The Soviet approach had worked precisely because it acknowledged resource constraints and designed within them. The reformers countered with uncomfortable statistics from the Western Front. American and British pilots in Thunderbolts and Mustangs had achieved kill ratios against German fighters that Soviet pilots could not match. American losses per sortie were substantially lower than Soviet equivalents. When Soviet pilots had flown Lend-Lease P-39 Airacobras, a relatively simple American design, they had achieved better survival rates than in Soviet fighters. Perhaps the American approach succeeded not despite its apparent inefficiencies, but because of the capabilities those inefficiencies enabled. The technical reports from Chkalov included combat performance data that made the reformers' case compelling. In the Pacific Theater, Thunderbolt pilots of the 5th and 13th Air Forces had achieved kill-to-loss ratios exceeding 10-1 against Japanese fighters. In Europe, Thunderbolt groups flying bomber escort and ground attack missions had lost fewer aircraft per 100 sorties than any other Allied fighter type. The P-47 had the lowest loss rate of any American fighter in the European theater, lower even than the celebrated P-51 Mustang. These statistics existed independent of piloting skill or tactical doctrine. They reflected aircraft capability translating directly into pilot survival. Soviet pilots, among the most skilled in the world after 4 years of brutal combat, were dying at rates that American pilots with far less experience avoided simply by flying aircraft engineered for survivability. The implications were stark and uncomfortable. Superior pilot training could not overcome inferior aircraft design. Individual skill could not compensate for systemic engineering advantages. Wars were won not by heroes, but by industrial systems producing survivable weapons in overwhelming quantities. Colonel General Pavel Zhigarev, commander of the Soviet Air Forces, visited Chkalov in January 1946 to observe Thunderbolt demonstrations personally. Stefanovsky flew the aircraft through a complete tactical profile, while Zhigarev watched from the ground and then from a chase aircraft. The demonstrations included high-speed passes, combat maneuvers, simulated ground attack runs, and a demonstration of the 8-gun armament against ground targets. After the flights, Zhigarev spent 2 hours in private meetings with the technical staff. His conclusions, while never publicly released, filtered through Soviet aviation leadership with profound impact. The Americans had created a fighter optimized not for aerial combat but for mission completion and pilot survival. The distinction was crucial. Soviet fighters were designed to win dogfights. The Thunderbolt was designed to destroy ground targets, escort bombers to distant objectives, and bring pilots home alive regardless of opposition encountered. In actual war, mission completion and survival mattered more than aerial victories. A pilot who destroyed 3 enemy fighters but died in the process had zero value for future missions. A pilot who destroyed 1 enemy fighter and survived could fly tomorrow and the next day and accumulate kills that far exceeded the dead ace. Zhigarev's report, too. Stalin emphasized an uncomfortable reality. The Soviet Union had won the Great Patriotic War by accepting casualties that would have been politically unacceptable to Western democracies. Soviet fighter regiments had been decimated and rebuilt multiple times. Pilots with just 20 hours of training had been thrown into combat because the need was desperate. This approach had worked because Soviet manpower seemed inexhaustible and because Nazi Germany was fighting on multiple fronts. But in any future conflict, particularly against the United States, such wastage would be strategically catastrophic. America's industrial capacity could produce aircraft faster than the Soviet Union could train replacement pilots. If American aircraft also ensured better pilot survival rates, the mathematical outcome was inevitable. Soviet losses would accelerate while American strength multiplied. The only solution was to adopt engineering approaches that prioritized survivability as highly as performance. The institutional resistance to this conclusion was substantial. Soviet design bureaus had evolved successful methodologies over decades. Yakovlev had perfected lightweight wooden construction techniques that enabled rapid production with limited aluminum supplies. Lavochkin had mastered aerodynamic refinement that extracted maximum performance from modest power plants. Mikoyan had developed high-altitude fighters using innovative engine designs. Each bureau had invested careers and reputations in their particular approach. Adopting American methodologies meant admitting that those approaches, while successful against Germany, might be inadequate against the United States. It meant acknowledging that resource constraints that seemed like virtuous efficiency were actually dangerous limitations. Most difficult of all, it meant accepting that some problems could not be solved through clever engineering, but only through abundant industrial capacity. The Thunderbolt's construction methods proved particularly challenging to Soviet manufacturing capabilities. Engineer teams from Factory No. 1, the Soviet Union's premier aviation plant, examined the aircraft's assembly techniques and found themselves confronting systematic differences in industrial philosophy. American construction relied on precision jigs, interchangeable parts, and standardized fasteners. Soviet construction relied on skilled workers fitting parts individually. American assembly assumed that components would arrive from subcontractors meeting exact specifications. Soviet assembly assumed that workers would hand-fit and adjust components during installation. American quality control used statistical sampling and go-no-go gauges. Soviet quality control relied on inspector judgment and experience. These differences reflected broader industrial realities. American factories operated with electricity continuously available, machine tools maintained to high standards, and materials supplied consistently to specification. Soviet factories dealt with interrupted power, worn machinery, and materials that varied in quality. American manufacturing could enforce tight tolerances because the entire industrial chain maintained those tolerances. Soviet manufacturing required loose tolerances because maintaining precision across thousands of subcontractors was impossible. The implications extended beyond just the Thunderbolt. If Soviet aviation wanted to adopt American survivability engineering, the entire industrial system would need transformation. Aluminum production would need to increase dramatically to support all-metal stressed skin construction. Machine tool quality would need improvement to achieve necessary tolerances. Electrical component manufacturing, virtually non-existent in the Soviet Union, would require development from nothing. Quality control systems would need systematic overhaul. Most challenging, the labor force would need retraining from the fashion of hand-fitting craftsmen to precision assembly workers. This was not just an aviation problem. This was a fundamental challenge to Soviet industrial methodology that had evolved since the 1920s. The Americans had not simply built a better fighter. They had revealed that their entire industrial system operated at a level of precision and standardization that the Soviet Union could not easily match. Lieutenant Colonel Balandin's engine analysis produced similar uncomfortable insights. The Pratt & Whitney R2800 was not inherently superior to Soviet radial engines in basic design. Soviet engineers understood supercharging, understood cylinder design, understood propeller reduction gearing. The difference lay in manufacturing execution. American cylinder machining maintained tolerances within 0.02 of an inch consistently across thousands of engines. Soviet machining achieved 0.005 in the best facilities, 0.010 in many factories. American bearing surfaces were ground and polished to mirror finishes. Soviet bearing surfaces were machined adequately but rarely polished. American valve seats were precisely matched to valve faces. Soviet valves were hand-lapped during assembly. Each small difference seemed minor. Cumulatively, they meant American engines ran smoother, cooler, longer, and more reliably. Soviet engineers could design engines matching American specifications on paper. Soviet factories could not manufacture them to the same standards. The gap was not knowledge, but industrial capability. The armament situation proved equally revealing. Captain Shelikov's team disassembled the Browning M2 machine guns and found themselves examining manufacturing quality that seemed almost excessive. Internal surfaces were polished to reduce friction. Moving parts had tolerances measured in thousandths of an inch. Springs were individually tested and matched. Feed mechanisms used hardened steel, machined to precise specifications. These were not just machine guns. They were precision instruments manufactured with jeweler's attention to detail, then produced by the thousands. Soviet aviation machine guns were effective weapons but showed rougher manufacturing. Internal surfaces were machined adequately but not polished. Tolerances were looser, requiring heavier parts to maintain reliability. Springs were manufactured to specification but not individually tested. The Soviet guns worked, but they required more frequent maintenance, suffered more jams in extreme conditions, and wore out faster. American guns reflected an industrial system capable of mass-producing precision. Soviet guns reflected an industrial system focused on adequate function at minimum resource cost. The Americans had achieved something the Soviet Union had not. They had made precision mass production routine rather than exceptional. In Soviet industry, precision manufacturing was reserved for critical applications like aircraft, engines, or tank transmissions, and even there, it required exceptional effort and skilled workers. In American industry, precision was standard across vast product ranges, from aircraft to automobiles to domestic appliances. This reflected decades of industrial development, massive investment in machine tools and measurement equipment, and systematic quality control training across the workforce. The Soviet Union had industrialized rapidly in the 1930s, building factories and training workers at unprecedented speed. But that rapid industrialization had prioritized quantity over quality, output over precision. The result was an industrial base capable of enormous production volumes but inconsistent quality. Fighting Germany, where industrial capacity was ultimately smaller than Soviet capacity, this approach had worked. Fighting America, where industrial capacity dwarfed everyone else, and quality standards exceeded Soviet capabilities, the approach might prove fatal. By summer 1946, the Thunderbolt evaluation had expanded beyond technical assessment into strategic analysis. The Ministry of Aviation Industry commissioned comprehensive reports comparing Soviet and American aviation industrial capabilities. The findings were classified at the highest levels, shared only with Stalin's inner circle, because they revealed vulnerabilities that contradicted public propaganda about Soviet industrial might. American aircraft production during the war had reached levels that Soviet planners considered almost fantastical. In 1944 alone, American factories had produced over 40,000 fighters, 14,000 bombers, and 10,000 transport aircraft. Total American wartime aviation production exceeded 300,000 aircraft. Soviet production, despite heroic efforts and enormous sacrifice, totaled approximately 160,000 aircraft, but raw numbers only told part of the story. American aircraft averaged substantially higher unit costs than Soviet equivalents, reflecting more complex construction and better equipment. A P-47 cost approximately $85,000 in 1944, equivalent to over $1 million in modern currency. A Yak-9 cost approximately $30,000 equivalent. Yet American factories produced Thunderbolts faster than Soviet factories produced Yaks. The explanation lay in industrial methodology. American factories used assembly line techniques borrowed from automobile manufacturing, with components manufactured by subcontractors and delivered to central assembly facilities. Soviet factories used more traditional methods, where most components were manufactured in-house and assembled by skilled workers hand-fitting parts. American methods required enormous upfront investment in tooling and coordination, but enabled rapid production by semi-skilled workers once established. Soviet methods required less upfront investment but demanded skilled workers throughout and limited production rates. The Americans had essentially bought production speed with capital investment. The Soviets had economized capital by accepting slower production and higher labor requirements. During the war, when both sides were fully mobilized, the American approach produced more aircraft. In peacetime, the American approach could be scaled down and then rapidly scaled up again because the tooling and methodology remained. The Soviet approach, tied to skilled workforce availability, could not be easily scaled. The strategic implications troubled Soviet leadership deeply. In any future conflict with America, the Soviet Union would need to compensate for inferior industrial capacity through superior tactics, better pilot training, or technological breakthroughs. But the Thunderbolt evaluation suggested that American engineering was rapidly eliminating tactical and training advantages through aircraft design that compensated for pilot limitations. And technological breakthroughs required advanced industrial capability to implement. The Soviet Union's historical advantages, vast territory and massive population that could absorb terrible casualties while wearing down invaders, would be less relevant in an air war where industrial production rates determined force strength. Stalin understood this analysis with characteristic clarity. His aviation commissar was instructed to prioritize three developments: aluminum production increases to enable all-metal aircraft construction, machine tool imports, or copying to improve manufacturing precision, and captured German jet technology to leapfrog American piston engine advantages. The Thunderbolt had revealed uncomfortable truths. The response would be systematic transformation of Soviet aviation industry, whatever the cost. The human dimension of the Thunderbolt evaluation often gets lost in technical details and strategic analysis, but it profoundly affected everyone involved. Major Stefanovsky, after 60 hours flying the aircraft, found himself psychologically conflicted. He was a patriot who had fought for the Soviet Union throughout the war. He believed deeply in Soviet aviation's capabilities. Yet he could not deny what the Thunderbolt had taught him. Western engineering had achieved things Soviet engineering had not. American industrial might was real, not propaganda. Most troubling, American design philosophy that seemed wasteful and inefficient actually produced better combat results than Soviet approaches that seemed more intelligent. These realizations did not make him less patriotic. Instead, they made him determined that the Soviet Union must learn from American successes while maintaining its own strengths. His final report included recommendations that Soviet designers study American construction methods while preserving Soviet emphasis on performance and efficiency. The goal should be synthesizing the best of both approaches, building aircraft that combined American survivability with Soviet agility, American reliability with Soviet simplicity. Engineer Colonel Yakovlev emerged from the evaluation with professional respect for American designers that bordered on admiration. The Thunderbolt's engineers had solved problems Soviet designers had barely acknowledged. They had created systems that worked reliably despite combat damage, extreme conditions, and minimal maintenance. They had built an aircraft that ordinary pilots could fly effectively after minimal training. These achievements reflected sophisticated engineering, not crude overbuilding. Yakovlev's recommendations emphasized that the Soviet Union needed to develop testing capabilities, matching American thoroughness. Soviet prototypes underwent relatively brief testing programs before production began, because war urgency demanded rapid deployment. American prototypes underwent months of systematic testing, exploring every performance, regime and failure mode before production authorization. This meant American aircraft entered service with fewer surprises and better understood limitations. Soviet aircraft often revealed problems only after units reported issues from combat operations. Building proper testing infrastructure would require investment and time, but it would produce better aircraft and save lives. Captain Shelekov's perspective shifted from skepticism to appreciation as the armament testing progressed. Initially, he had considered 850 caliber machine guns an inefficient solution, inferior to cannon armament. But watching the test footage of ground targets being obliterated by concentrated fire, he began understanding the philosophy. The Americans had prioritized reliability over power, volume over precision, sustained firepower over explosive impact. In combat, when adrenaline affected pilot accuracy, when targets appeared briefly and unpredictably, when mechanical failures could be fatal. Thunderbolt's approach proved superior. 8 guns meant redundancy. If 2 jammed, 6 still fired. Massive ammunition load meant pilots could fire longer bursts, compensating for poor deflection shooting. 50 caliber rounds lacked cannon shells' explosive impact, but their ballistic consistency made aiming easier. Shelekov's recommendations called for Soviet designers to reconsider the rush toward heavier cannon calibers. Perhaps maintaining multiple lighter weapons with abundant ammunition served combat reality better than mounting fewer heavy weapons with limited ammunition. The legacy of the Thunderbolt evaluation extended far beyond the immediate post-war years. Soviet fighter designs from the late 1940s onward showed clear American influence. The Lavochkin La-15, entering service in 1949, featured all-metal construction and much heavier structural design than earlier Lavochkin fighters. The Mikoyan Gurevich MiG-15, which would shock the West, in Korea, incorporated lessons about durability and systems redundancy learned from American aircraft evaluation. Pilot armor, self-sealing fuel tanks, and duplicate control systems became standard in Soviet fighters, directly reflecting Thunderbolt analysis. The Yakovlev Yak-23, a lightweight fighter that seemed to reject American heavy engineering, still featured improved structural strength and better systems protection than earlier Yak designs. Even when Soviet designers chose different solutions, they were now solving problems the Thunderbolt had highlighted. The industrial transformation Stalin ordered proceeded through the late 1940s and 50s, constrained by Cold War tensions and limited resources, but nonetheless reshaping Soviet manufacturing capabilities. Aluminum production expanded dramatically. Machine tool factories received priority investment. Quality control methodologies, borrowed from captured German documentation and observed American practice, gradually spread through Soviet industry. The transformation was incomplete and uneven, with many factories maintaining traditional methods into the 1960s, but the direction was clear. Soviet industry was pursuing precision and standardization that American industry had achieved decades earlier. The Thunderbolt had been a teacher whose lessons echoed through Soviet aviation for generations. The Thunderbolt's influence on Soviet aviation thinking extended into unexpected domains. By 1947, Soviet ground attack aviation was undergoing systematic re-evaluation based partly on lessons from the American fighter bomber. The Ilyushin Il-2 Sturmovik had been the Soviet Union's iconic ground attack aircraft during the war, heavily armored and devastating against German tanks and infantry. But the Il-2 was slow, vulnerable to fighter interception, and limited in operational flexibility. The Thunderbolt had demonstrated an alternative approach. A fighter optimized for speed and altitude could transition to ground attack role, deliver devastating firepower, and escape fighter interception through superior performance. This multi-role capability reflected American tactical flexibility that Soviet doctrine had not emphasized. Soviet aircraft tended toward specialization. Fighters fought fighters. Ground attack aircraft attacked ground targets. Bombers bombed. The Americans had created aircraft that could perform multiple roles effectively within a single mission. The implications for Soviet tactical aviation were profound. Specialized aircraft required specialized training, specialized maintenance, and specialized logistics. A fighter regiment needed different support than a ground attack regiment. Airfields needed to accommodate multiple aircraft types with different requirements. Combat operations required coordination between different aviation branches with different capabilities and limitations. The American multi-role approach simplified everything. A Thunderbolt squadron could fly bomber escort in the morning, ground attack in the afternoon, and fighter sweep in the evening using the same aircraft and pilots. Support requirements were consistent, training was unified, logistics were simplified. This operational flexibility had contributed significantly to American air power effectiveness. Soviet commanders who had cooperated with American units during the final months of the war reported that American air groups could shift missions rapidly based on battlefield requirements, something Soviet aviation found difficult due to specialization. General Georgy Zakharov, who had coordinated with American 9th Air Force units during the link-up at the Elbe River, submitted observations that influenced Soviet post-war aviation doctrine. American fighter groups he observed in Germany routinely flew 4 different mission types daily: bomber escort, armed reconnaissance, ground attack, and defensive patrols. The same aircraft executed all missions. The same pilots flew all profiles. When ground commanders requested air support, American fighters overhead could respond immediately, regardless of their primary mission. Soviet aviation required requesting specific aircraft types, waiting for their arrival, and coordinating their brief presence over the target. The Americans had achieved responsiveness through flexibility. The Soviets had created delays through specialization. Zakharov recommended that future Soviet fighters be designed for multi-role capability, even at the cost of some specialized performance. A fighter that could perform 3 missions adequately proved more valuable than 3 specialized aircraft, each performing one mission excellently but unable to assist with the others. The Thunderbolt evaluation also influenced Soviet understanding of pilot training requirements. American pilot training emphasized standardization and systematic skill building. Pilots progressed through defined stages: primary training in light aircraft, basic training in more capable aircraft, advanced training in training versions of operational aircraft, and finally transition training in their assigned fighter type. At each stage, performance standards were clearly defined and consistently enforced. Pilots who failed to meet standards at any stage were reassigned to other roles. This systematic approach produced pilots with consistent baseline competency, though not necessarily exceptional skill. Soviet training was less standardized and more variable in quality. In the desperate years of 1941 through 1943, pilots had been rushed through abbreviated training to replace catastrophic losses. Some pilots reached operational units with barely 20 hours total flight time. Others received thorough training lasting months. The result was enormous variation in pilot quality, from exceptional aces to barely competent novices, all flying the same aircraft types in the units. The Americans had matched their systematic training to aircraft capability. The Thunderbolt was designed to be survivable even with mediocre pilots. Soviet fighters required skilled pilots to survive. This difference reflected strategic realities. America could afford lengthy training programs because their homeland was unthreatened and time was available. The Soviet Union, fighting for survival on its own territory, could not afford such luxury. But in any future conflict, the Americans would maintain their systematic training advantage, while the Soviets would no longer have existential desperation to excuse abbreviated training. The solution required either developing training capacity matching American standards or designing aircraft even more forgiving of pilot limitations than American equivalents. Soviet aviation leadership chose to pursue both paths simultaneously, expanding training facilities and duration, while also emphasizing survivability in new aircraft designs. The goal was reaching American baseline pilot competency, while maintaining Soviet emphasis on exceptional individual achievement that produced aces. The political dimensions of the Thunderbolt evaluation created complications that technical staff had not anticipated. By late 1946, as Cold War tensions increased, admitting American technological superiority became ideologically problematic. Stalin's propaganda emphasized Soviet accomplishments and minimized Western achievements. Soviet scientists and engineers were supposedly the world's finest. Soviet industry was supposedly advancing faster than capitalist economies. Acknowledging that American aircraft engineering exceeded Soviet capabilities contradicted official narratives. The technical reports from Chkalov were therefore classified at levels exceeding normal military secrecy. They became politically sensitive documents whose conclusions could not be publicly acknowledged. Engineers who had praised American design. Approaches in 1945 found themselves unable to cite those conclusions in 1947 without risking accusations of insufficient patriotism. The Thunderbolt itself was quietly removed from active testing and placed in storage. Its presence was an uncomfortable reminder of American capabilities that official ideology now required downplaying. This politicization of technical assessment damaged Soviet aviation development in subtle but significant ways. Engineers learned to frame their recommendations carefully, emphasizing Soviet achievements while gently suggesting improvements that happened to mirror American approaches without explicitly citing them. Design bureaus competed for resources partly through political connections rather than purely technical merit. Promising concepts could be rejected if they seemed to validate Western approaches too explicitly. The result was innovation constrained by ideological acceptability. Some excellent Soviet designs emerged, despite these constraints, testifying to the talent and dedication of Soviet engineers. But the constraints existed, slowing development and sometimes preventing optimal solutions from being pursued. The Thunderbolt evaluation had revealed technical truths, but political requirements forced those truths to be expressed indirectly and implemented incompletely. Soviet aviation would spend decades working around this contradiction, achieving remarkable results while always wondering what might have been possible with complete intellectual freedom. The human costs of this political sensitivity affected individuals who had participated in the evaluation. Major Stefanovsky continued as a test pilot, but found himself unable to publicly discuss his Thunderbolt experience. His recommendations appeared in classified documents that few read. His professional reputation rested on testing Soviet aircraft, while his most educational experience remained secret. Engineer Colonel Yakovlev faced similar constraints. His detailed analysis of American construction methods existed in reports that could not be widely distributed. When he proposed manufacturing improvements based on that analysis, he carefully avoided mentioning their origin. Captain Shelikov's armament recommendations were implemented selectively, with successful elements credited to Soviet innovation, while aspects that failed were quietly dropped without acknowledging they had come from studying American designs. This was Soviet technical development under ideological constraint, achieving progress through indirect routes and unacknowledged borrowing, and less efficient than straightforward learning, but still effective enough to maintain Soviet aviation as a credible force. The broader strategic implications of the Thunderbolt evaluation shaped Soviet military planning throughout the late 1940s and early 50s. Soviet military theorists understood that, in any conflict with the United States, American air power would be formidable. American strategic bombers could potentially deliver atomic weapons against Soviet cities. American tactical aviation could devastate Soviet ground forces. American air defense could make Soviet bomber attacks prohibitively costly. The solution required developing capabilities to counter American advantages. Soviet designers began developing jet fighters earlier than sometimes recognized, not just because German technology became available, but because the Thunderbolt evaluation had demonstrated that Soviet piston-engine fighters could not match American capability. Jets offered potential leapfrogging, achieving performance that made American piston-engine advantages irrelevant. The MiG-15's rushed development and deployment reflected urgency, created partly by understanding what American piston fighters could do and imagining what American jets might achieve. Soviet air defense systems received enormous investment in this period, building integrated radar networks, command and control systems, and fighter direction capabilities that would eventually surpass American equivalents. This investment reflected understanding that Soviet airspace could not be defended by aircraft alone, regardless of their capability. American bombers with American fighter escorts would overwhelm any purely fighter-based defense. Only integrated systems combining radar detection, ground-controlled interception, and anti-aircraft artillery could provide adequate protection. The Thunderbolt evaluation had not directly addressed air defense, but it had demonstrated the capability of American combat aviation. Soviet planners extrapolated from the Thunderbolt's ground attack effectiveness to imagine American bomber formations with similar durability and firepower. The conclusion was unavoidable. Soviet air defense required systematic development at a scale matching the entire Soviet aviation industry. Stalin authorized resources accordingly, creating the foundation for air defense systems that would eventually place Soviet cosmonauts in orbit using technology developed originally to shoot down American bombers. The Thunderbolt's legacy appeared most directly in Korean War combat, where American and Soviet aviation clashed directly for the first time. Soviet pilots flying MiG-15 jets against American aircraft, including late-model Thunderbolts still in service with some units, discovered that lessons from the Chkalov evaluation proved accurate in combat. American aircraft were indeed remarkably durable. American pilots indeed exploited dive performance to escape engagements. American formations indeed delivered devastating firepower when allowed to concentrate fire. Soviet pilots achieved kill ratios that seemed favorable in raw numbers but reflected exchange rates that would be strategically unsustainable in extended conflict. Soviet aircraft losses could be replaced only slowly. American losses were replaced almost immediately, from massive reserves. This was the strategic reality the Thunderbolt evaluation had predicted. American industrial capacity translated directly into military sustainability. Soviet qualitative advantages in some areas could not overcome American quantitative dominance across all areas. The Chinese and North Korean pilots flying Soviet aircraft discovered even more dramatically what the Thunderbolt evaluation had revealed. American aircraft flown by adequately trained pilots consistently defeated Soviet aircraft flown by poorly trained pilots. Skill mattered, but it could not overcome systematic aircraft capability differences. American pilots in inferior aircraft often survived encounters with superior Soviet jets because their aircraft absorbed damage and continued flying. Soviet-trained pilots in superior jets often died after relatively minor damage because their aircraft lacked the redundancy and durability that American design philosophy emphasized. The kill ratios reflected these realities. American pilots achieved approximately 10-to-1 exchange rates against Chinese and North Korean pilots, numbers that echoed Pacific War statistics against Japan. Even against Soviet pilots, where training and experience were more comparable, American pilots achieved favorable exchange rates through aircraft capability more than pilot skill. The Thunderbolt evaluation's predictions about survivability, determining combat outcomes, proved accurate in the most definitive test, actual combat. Soviet aviation designers drew additional lessons from Korea that refined insights from the Thunderbolt evaluation. American aircraft maintenance in combat conditions was vastly superior to Soviet equivalents. American fighters maintained high operational readiness rates despite intensive combat operations. Soviet fighters required extensive maintenance and showed declining readiness rates during sustained operations. This reflected design philosophy differences. American aircraft were designed for easy maintenance with accessible components, standardized tools, and simple procedures. Soviet aircraft were designed for performance with maintenance as a secondary consideration. The result was American aircraft spending more time combat-ready and less time being repaired. Soviet designers began incorporating maintainability into design requirements explicitly, rather than treating it as an afterthought. The Thunderbolt's accessible engine, its panel designs that could be removed with standard tools, its systems that could be checked quickly and replaced easily, all became reference points for Soviet designers trying to improve maintainability without compromising performance. The final irony of the Thunderbolt evaluation emerged only decades later when archives opened and former Soviet engineers could speak freely about their wartime and post-war experiences. The Thunderbolt had been profoundly influential on Soviet aviation development, yet officially it had never existed in Soviet service. No public records acknowledged its evaluation. No Soviet aviation history mentioned its impact. Engineers who had learned critical lessons from studying it could not cite it as their source. The aircraft that had revealed American industrial and engineering capability remained officially invisible, a secret teacher whose lessons appeared anonymously in Soviet designs. This reflected the tragedy of Soviet technical development during the Cold War. Talented engineers learning from global best practices, but unable to acknowledge those sources. Excellent designs incorporating foreign innovations that could not be credited. Progress achieved through indirect paths and unacknowledged borrowing that was less efficient than open exchange would have been. When former test pilot Stepan Mikoyan, nephew of the famous designer, finally published his memoirs in the 1990s, he included a chapter on foreign aircraft evaluation that mentioned the Thunderbolt assessment. His conclusion captured the evaluation's true significance better than any technical report. The Americans had built an aircraft that forgave mistakes, absorbed punishment, and brought pilots home. They had engineered survival into every system. They had created a weapon for citizen soldiers, not elite warriors. That was their genius. They understood that wars are won by industrial systems, producing adequate weapons in overwhelming numbers, operated by adequately trained personnel who survived to fight again. We Soviets had created beautiful aircraft for exceptional pilots. The Americans created adequate aircraft for ordinary pilots. In sustained conflict, their approach proved superior. We learned this lesson at enormous cost. The Thunderbolt taught it to us clearly, but pride prevented us from learning it fully. That hesitation cost Soviet lives in Korea and shaped our aviation development for decades. The Republic P-47 Thunderbolt that Major Stefanovsky flew in, the summer of 1945, now sits in storage at the Central Museum of the Air Force at Monino, outside Moscow. Few visitors notice it among more dramatic Soviet aircraft. Tour guides rarely mention it. Yet that weathered aircraft changed Soviet aviation more profoundly than many aircraft that appear in official histories. It demonstrated that American engineering philosophy, seeming crude and wasteful, actually produced superior combat results. It revealed that industrial capacity and manufacturing precision mattered as much as aerodynamic elegance. It showed that democratic nations, emphasizing individual survival, could create weapons more effective than authoritarian nations, accepting casualties as acceptable costs. These lessons, learned quietly in test flights over Moscow, rippled through Soviet aviation for generations, shaping fighters, training programs, industrial processes, and strategic thinking in ways rarely acknowledged but deeply consequential. The Americans had built more than a fighter. They had built a statement about industrial democracy's capabilities. Soviet engineers studied that statement and understood its implications with clarity that politics forced them to express only indirectly. The Thunderbolt evaluation was thus both technical assessment and ideological challenge, revealing not just American aircraft capability, but the strengths of the system that produced such capability. Up next, you've got two more standout stories right on your screen. If this one hit the mark, you won't want to pass these up. Just click and check them out. And don't forget to subscribe and turn on the notification bell so you don't miss any upload from us.